All right. So in this chapter, we'll talk about applications of Newton's laws. Okay. So you studied 3 Newton's laws in the previous chapter, and we'll apply those 3 laws to various situations. Okay. So let me start off by reviewing the 3 laws. Okay. I'll come back to Newton's first law in a second. Here's Newton's second law. Okay. What it says is the net force acting on an object. Okay. Well, what it's saying is forces give objects an acceleration. And when an object is accelerating, what does that mean? Its velocity is changing. Okay, so that's what this law says. So, and what do you mean by net force? So for instance, here's an object where 4 forces are acting on it. 1, 2, 3, 4. Okay. The net force is just the vector sum of these forces. Okay. And what this is saying is the acceleration is in the same direction as the force. Yep. So the acceleration is proportional to the force. Greater the mass of the object, smaller its acceleration. Okay. So it's saying all of that. And of course, this is the vector equation. So what that means is the x component of this vector is equal to the x component of that vector. Y component is equal to y component. So in 3 dimensions, this is really 3 equations. Okay. And you saw that last time. So the x component of the force gives an acceleration in the x direction. Okay. So a force in the x direction does not affect motion in the y direction or z direction. Okay. So the Newton's second law is really 3 equations in 3 dimensions. Okay. The first law is a special case of the second law. If the net force is 0, if the net force acting on the object is 0, acceleration is 0. And if acceleration is 0, that means the velocity is constant. Okay? And that's Newton's first law. Yep. So Newton's first law says when a 0 net force acts on an object, its velocity is constant. Okay? And again, this law was really discovered by Mr. Galileo, but we call it Newton's first law because it's a special case of the second law. Okay. We're just reviewing this. You've seen this before. Okay. We will be interested in applying these laws. Okay. Now, the third law says the following. Whenever 2 objects interact, so for instance, this swimmer is interacting with the wall. Okay. So whenever 2 objects interact, and every object interacts with every other object in the universe. Okay, we have one of 4 forces. Okay. So we have strong force, weak force, electromagnetic force, or gravity. Okay. Now to interact via the strong or the weak force, you have to be really close. Okay. But to interact via electromagnetically or gravity, you can be far away. Okay. So anyway, this object is interacting with this object. And what do we mean by interacting? Well, this object is exerting a force on this on the wall. And what Mr. Newton says is, if one object exerts a force on the other object exerts an equal and opposite force on the first object. Okay. So the forces are on different objects, but they're of equal magnitude and opposite direction. Okay. That's Newton's third law. All right, so we are going to apply these 3 laws to various situations. Okay? And so let's look at some applications. So here's the first application. Okay, you come across these things every day. Okay? And obviously, well, this is a heavy object hanging on this wire, and you don't want this falling, right? I mean, this thing falls on a car and you have a lawsuit waiting to happen. Besides the fact somebody might get injured. Okay, so in analyzing these objects, okay, so if you want this object to be at rest, that means its acceleration is 0. That means the sum of all the forces acting on it must be 0. Okay? And that's how we are going to analyze it. Okay? So you want this object to be at rest. Okay. So let's look at all the forces acting on the object. Okay. Now in this particular case, actually what you want is to analyze the knot there, but we'll come back to that in a second. Okay, so let's say that knot needs to be at rest. Okay. Gravity is pulling down on this, which is pulling down on the knot. There's tension in the string there and there. Okay. So now in this diagram, the author treats this as a point object. Okay. And that's what we call by the free body diagram, but it's more correctly the knot that is the point object. Okay. Now, if you don't want this falling, you don't want the knot moving. So what are the three forces on the knot? The weight of the object, the tension in the string, and the tension in this string. There's the tension in that string. All right, so if you don't want the knot to move, that means that these three forces should add up to 0. Okay? And that's the analysis of the situation. Okay? So what this tells you is, so if you figure out what is the weight you want to hang, then you can calculate the tension in these strings, and that will tell you how strong the strings need to be. Okay? And that would be the point of these problems. So if you're an engineer building this suspension system, that tells you what kind of suspension system you've got to build. Okay? All right, so again, if the three forces have to add up to 0, what that means is, so there is this first force, there is the x component, there is the y component, there is the second tension, x, y component, and there's the weight, which doesn't have an x component. So if these three forces are to add up to 0, this x component must cancel that x component. These two y components must cancel this y component. Okay? And then the three forces would add up to 0, and that would be in equilibrium. Okay? All right, so this term free body diagram. So here was the physical system that you were analyzing. Okay? And we want to draw very simple diagrams and show the relevant forces. So this system, your object of interest was represented by a point, and the three forces were shown. Okay? Now, right now, initially what we'll be considering is all the forces acting on the system will be going through the center of mass of the object. I haven't told you what that means, but you sort of have an intuitive idea. And then you can represent the object as a point object. Okay? So we'll be considering situations where this object is not spinning. Okay? The only kind of motion it'll have is linear motion. All right, so for now we can treat the object as a point object. When we come to rotational motion in chapter 9, then we won't be treating the object as a point object. Okay? So right now, the underlying assumption is all the forces go through the center of mass, and that's why in this particular situation, you have to consider the knot. But anyway, here's the free body diagram, just showing you the essential things, which the forces and the object of interest is represented as a point object. Okay. Here's the second situation. Okay. So, for instance, here is a barge, and these two tugboats are applying a force on the object. And you see this force is going through the center of mass, and this force is going through the center of mass. Okay. For instance, if this tugboat was pushing over here, what would happen? Then this would rotate. Okay, so right now we're not going to consider that situation. So we're going to consider only situations where the forces act through the center of mass. Okay, so this tugboat, so the free body diagram is, so here's the physical picture. The free body diagram is, this is the free body diagram. Okay, your object is represented by a point. The force that this boat exerts is there. The force that this boat exerts is there. What is this guy? I'm sorry? So that's the friction force between the barge and the water. So that's the drag force. Okay. So there are three forces acting on this barge. Okay. Now, if it's accelerating, what does Newton say to you? If it's accelerating, if the acceleration is not zero, that means that there must be a net force acting on the object. Okay. And so the sum of these three forces is not zero. The sum of these three forces is the net force, and that's equal to mass times the acceleration of the object. Okay. And that's what you'll be doing. Okay. So in this case, how many dimensions is the motion in? 2 dimensions. So that equation is really 2 equations. Okay. So the x component of this force should equal the x component of the acceleration, and y component of this force should equal y component of the acceleration. Okay. All right. So so there is the net force. There's F1, F2. This is the applied force. There's the drag force, and there's the net force. Okay. And what direction will the acceleration be in? Which direction will this object accelerate in? In the direction of the net force. So the object will accelerate in that direction. Okay. All right. So again, what does the free body diagram do? In our case, for non-rotating object, it draws the object, relevant object, as a point object, and shows you all the relevant forces. Okay. And then you apply Newton's laws to the motion of that object. Okay. All right, so now we'll consider this situation. Okay, so there are several objects here. There's this guy, and there's the whole elevator, and so on. Okay, so depending on what object you want to analyze, you represent that object. So if you wanted to look at the motion of the elevator, you look at all the forces applied to the elevator. So here is the tension in the rope that's by which the elevator is hanging, and there's the force of gravity on the elevator. Okay, so the total force of gravity on the elevator. So if you wanted to analyze the elevator, the two forces you would be looking at is that. So the total force of gravity on it. Okay. If you wanted to analyze the person, what are the forces acting on the person? You just look at the forces just acting on the person.
The force of the elevator going up and then the weight of the person.
Okay, so the only forces that will act on the person is, okay, the force of gravity. Earth is attracting you no matter where you are. And then what is the only other object that's in contact with the person? This scale that he's standing on. And the scale is pushing him up. Okay, so if this guy is the person, that's the weight of the person, and this is the force of the scale. We'll call it the normal force. Okay. So that is the free body diagram for this guy, and this is the free body diagram for this guy. Okay. All right. So, so depending on what object it is that you're analyzing, okay, you draw a free body diagram for that. Okay. So the motion of the elevator, these forces will determine the motion of the elevator, and these forces will determine the motion of the person. Okay. All right. So now here's another system. Okay. Here's a mass. Right now, it's sitting on a frictionless table top. For now, we'll keep things simple. We'll say the pulleys are frictionless and massless. What that means is the tension in either side of the strings is the same. When there is friction and friction will be hard to account for, so we won't do that. When the mass of the pulley is not negligible, then the tensions will be different. Okay, so but for now, we'll say this is massless, so the tension is the same. Okay. Now, if you have multiple objects, you apply Newton's laws to in each object independently. Okay. So let's look at this object. What are the forces on this object? There's the force of gravity, the normal force, and the tension. There are three forces acting on this object. So that object, there's the weight, force of gravity, there's the normal force, which is the table pushing up on it, and there's the tension there. And now, is this object coming off the table? Is it moving in the y direction? No. So obviously, right away, right off the bat, this is very elementary, and you know that this force is equal to that. The net force in the y direction is 0, and that's why it's not moving in that direction. Okay. It was at rest in that direction, and so it's not moving. So the net force is this tension, which will give it an acceleration in that direction. Here's the second object, and let's look at all the forces acting on this object. There's the force of gravity, and the tension is pulling on this object in that direction. So that's the tension. Okay, there's the tension. All right, so the two forces acting on this object are its weight and the tension. Okay, and you understand that since these guys are tied together, the magnitude of this acceleration will equal the magnitude of that acceleration. Okay, so you would apply Newton's laws to both objects independently. Okay, so if I were to write the magnitude of the forces, so in this case, this would be m2g minus tension is equal to m2 times a. That would be the equation of motion for this guy. The equation of motion for this guy would be T equal to m1a, where a is the magnitude of the acceleration. Okay. And so now if you knew the two masses, m1 and m2, you could solve for the tension in the string and the acceleration of the objects, since you have two equations and you could solve for the two unknowns. Okay. So you guys understand this? All right. So here's a device called Atwood's machine, and we will do an experiment in lab using this machine, and let's see what this thing is about. Okay. Again, we keep things simple. We'll say the mass of the pulley is negligible, okay, and it's frictionless. So when you say that, what does that mean? We've said this 2-3 times now. That's right. So the tension in the string is going to be the same. If the mass is not negligible, then the tensions would be different. Okay? And you will see that in your junior level statics course. Okay? But right now, we will keep things simple. Okay, so the tension is the same. Okay, so for now, let's say this guy is heavier, and so this guy will fall down. So the acceleration will be in this direction, and this guy, the acceleration will be in that direction. Those are the vectors. Of course, the magnitude of the acceleration will be the same, and we'll call it A. Okay. Now, here are two different objects. Again, you apply Newton's laws to both the objects independently. Okay, so for this guy, there's the tension, and there's m1g. This is m2g, and tension in that direction. All right, this fella is falling down in this direction, so we'll take that direction to be the positive, and the magnitude of that is A. So m2g minus t equal to m2 times A. So here is the equation of motion for this guy. That's what law did we apply? We applied Newton's second law. The net force is mass times the acceleration of the object. So that's the law we are applying. Okay. For this guy, it's tension minus m1g m1 times A. Okay, so for this guy, we took that as the positive direction. Tension minus m1g was equal to mass times the acceleration. All right, now here you have two equations. If you're given the mass m1 and m2, you can solve for tension and the acceleration. Okay, so let's solve for the magnitude of the acceleration. We'll add the two equations, and I'll show you the point of this guy. You add these two equations, this will cancel. What you get is m2 minus m1g equal to m1 plus m2a.
Does that say so? The top right, the negative, what is that? After the negative?
That's tension, right?
Is that a T?
All right, so solving for A, m2 minus m1 g divided by m1 plus m2. All right, well, what did this do for us? Okay, so let's look at A. Now, A, if m2 is equal to m1, if m2 is equal to m1, what is A? 0. A is 0. Okay? So if you set it in motion, it'll maintain its constant motion, but the acceleration will be 0. What will happen if m1 is 0?
It would be focused on M2,
Mhm.
biased towards M2.
Well, can you tell me what A will be? So if m1 is 0, this is 0. This term will be 1. A will be equal to g.
Yeah.
Okay? So here is a device where you can dial acceleration anywhere from g to 0 by changing the values of m1 and m2. And that was the point of Mr. Atwood. Okay? So here's a device where you could simulate whatever acceleration you want. You want the acceleration on the moon, you adjust the two masses accordingly. Okay? You want the acceleration, any value between 0 and g. Okay? And actually what you can, if you think about it, if m2 is 0, it would accelerate that way, so this can actually go between minus g and g, if you want to think of it that way. Okay? All right, so that's Atwood's machine. He is giving you an acceleration anywhere between 0 and g. Okay? All right, now we'll talk about friction forces. Okay, so let me pull up an application because I'm sort of recording these lectures as well. So if I show you here in real life, I can't record that. All right, let's see where are the friction forces. Where's the friction app?
I think it's above,
Where?
above gene expression, function level, bottom left.
Okay. I don't want that one. Let's see. Yeah, that's the one I was looking for. All right, so let's look at this. Okay. I'm going to push, oops. Okay. See, I'm pushing on the box And you can see the applied force is the brown colored force, but the object is not moving. And so Mr. Newton says there must be an equal and opposite force, and that's the friction force. And how's the friction force coming about? Because the two surfaces are in contact. And so the friction forces arise because the atoms of the box are attracted to the atoms of the ground. Okay, so you try to push the box in this direction, and there's a friction force in this direction. Okay. What if I had tried to push the box in this direction, and it's not moving? Then the friction force would be in the opposite direction. Okay. And similarly, if it's moving in that direction to the right, you see the friction force is in the left, toward the left. If the object is moving to the left, the friction force is to the right. Okay, so friction forces are always in the opposite direction of the motion. Okay? And how do they arise? They arise because of the attractive forces between the two objects. Okay. Now the term friction force is used when two solid objects rub against each other. But let's say if you throw a tennis ball through the air, there is a friction force on the tennis ball in the direction opposite to the motion, but that force is called a drag force. Okay? So when an object moves through a fluid, that's called a drag force. Okay. So for instance, half the gas that you spend in your car is because you're moving through air. Okay? Now, if you could carry a tank of oxygen and fuel in your car and drove on the moon, for instance, you could double your gas mileage, everything else being equal. Okay? Yep.
Is the friction force between two objects always going to be constant, or does it change depending on the applied force?
Okay, so we'll see once it's moving, it's constant. Okay, so that's called the kinetic friction force. That is constant. But let's say I apply a static friction force. So right now I will apply a force of, you can see that I've applied a force of 30 newtons, and the friction force is equal to that. See, the static friction force can increase, and it increases up to a maximum value. And once the object breaks loose, now it doesn't matter what the applied force is, the friction force remains constant. Okay? So once the object is moving, that friction force is called a kinetic friction force, and that kinetic friction force will be constant. Okay? Between these two objects, can you think of any way to increase the friction force? Okay, so the friction force depends on the two surfaces that are in contact.
Increase the surface area?
I'm sorry? Well, you're not changing the surface properties of the surface. Yep.
Would it be adding more weight?
Yep. So if you push down on the object, okay, you'd presumably get more atoms to attract each other. Okay? So adding weight would increase the friction force. Okay? Yeah. See, the friction force increased. Yeah. I guess what I'll do is, okay, you see that? Okay, the surfaces didn't change, and the friction force, so the normal force, so the friction force, it turns out, so the weight of the object is acting this way, and the normal force will be in the opposite direction. So the friction force, it'll turn out, will be proportional to the normal force. Okay? So we'll see all of that. Okay, so let's look at friction. Okay, so the term friction again is used when two solid objects rub against each other. Okay, if an object is moving in a fluid, then that's called a drag force. Okay, all right. What direction does the friction force act? Always opposite to the direction of motion. Okay, all right. So, so if here are two surfaces in contact, and if you look at them, look at it magnified, okay, it's no matter how smooth the objects surfaces are, they'll always be jagged, and the friction force arises from the bonds, the loose bonds. Okay, so if you're trying to move the object to the right, you have to break these bonds which are pulling back the object in this direction. That's the friction force. So part of the friction force is because of the roughness of the surfaces in contact. However, much of the friction force is due to the attractive forces between the molecules of the two objects. Okay. In fact, for perfectly smooth surface of similar material would adhere, forming a cold well, and and then you pretty much have to break the object for the two objects to move. Yeah. So the friction force would be large. The friction force depends on the surfaces in contact and how hard they're being pushed against each other. The harder you push against each other, the greater the bonds and the greater the friction force. Okay? So here's an interesting fact. Two rough surfaces in contact have a much smaller area of actual contact than the total area. So the actual contact area is what matters. So in fact, the surface, the friction force is essentially independent of this surface area. Okay. When two surfaces are in contact, the actual microscopic area of a contact is only of the order of 1 part in 10,000. What that means is when your textbook is sitting on the table, the actual area of contact is roughly equal to the size of a ballpoint pen head, okay, or a pencil tip. Yeah, so the area of contact is very small. All right, so you saw I showed you the app. Okay. So here's an object. Let's look at all the forces acting on the object. Here's the weight of the object. Here's the gravity, earth pulling down on the object. Here's the normal force. Where's the normal force coming from? The table pushing up on the object. Okay. And right now we have applied this force, let's say 10 newtons, and the object is not moving. And that's because this static friction force is equal to it. Okay, that's preventing it from moving. Let's say I apply a 15 Newton force. The static friction force increased to 15 newtons, and the object didn't move. If I didn't push on this object, what is the static friction force? 0. I applied 15 newtons, this became 15 newtons. I applied 20 newtons, this became 20 newtons. How did that increase? How did that increase? How did that friction force arise? So the atoms on the table are pulling on the atoms on the box. So if you ask them to pull harder, they were pulling harder. But there's a limit to how hard they can pull. Right? So if you apply a great enough force, then you'll break those bonds and the object will start moving. Okay? So that greatest force that the two surfaces can sustain is the maximum static friction force. Okay? And that's what this graph is telling you. Okay? So this is the force you apply. This is the static region. If you apply a force this big, the static friction force is equal to that, and the object doesn't move. Okay? When you apply this larger force, you've reached the maximum static friction force, and you'll just break loose. All right, so let me show you that. Show that to you on the app. Okay, so you see 60 newtons. Monitor this. Okay, so 67 newtons. It's not breaking loose. So 115, So we're still below the maximum static friction force. Okay. So the maximum static friction force for those two guys were around 125 Newton. Okay. What would happen if I put glue underneath that box?
Static forces go up.
I'm sorry?
The static forces go up.
Yep, exactly. Okay. So the static friction force would increase. Yep.
So for the time that you're pushing on this thing and applying force before it actually moves,
Mhm.
to break the static friction,
Mhm.
you're still expending energy, right? To apply the force to attempt to move it?
Yeah, well, okay, so that's an interesting question. So technically, you're not doing any work and you're not spending any energy, but your muscles are compressed, and so. But yeah, so how does it relate to the situation?
I was more curious of like how the energy would be expended if you weren't actually moving.
So your muscles are contracted and it's all turning into heat, and none of it is going into the motion of the object. Yeah. All right. All right, so the important thing to understand is there's a maximum static friction force. Okay? And we'll do a calculation to that. Okay, so there's a maximum static friction force, and if you apply a force greater than that, then the object will break loose, and this is the kinetic friction force. And you see, no matter how large the applied force, the kinetic friction force is constant. Once the object starts moving, the friction force in this direction, that remains constant. It's independent of how large this force is. Okay? The larger this force is, since this is constant, the larger this force is, the acceleration would be greater.
Is the kinetic friction force usually lesser than the static?
It's always less than the static friction. Okay? All right, so we saw that in that. Okay, so I'm going to apply a force. We still haven't reached the maximum static friction force. And you see now the applied force is greater, but this kinetic friction force is not changing. Okay? All right, so the kinetic friction force is constant. All right. Now it turns out that these forces are proportional to the normal force. Okay? And if this is sitting on a horizontal surface, the normal force is equal to the weight. Now, of course, if you push down on the object, the normal force will increase. Okay, so that's a way to increase friction force. Okay. But the friction force is proportional to the normal force. And the proportionality constant is called mu k, the coefficient of friction. Okay. Mu is called the coefficient of friction. And if it's mu k, that's kinetic coefficient of friction, and mu s is the static coefficient of friction. Okay, and since mu f max is always greater than that, that means mu s is always greater than mu k. The static coefficient of friction is always greater than mu k. Okay, and these coefficients are important where you have tables of these values for various surfaces, and I'll show the tables to you in a second. Okay, and all right. Can anybody tell me the dimensions of these guys? What are the units in which mu is measured? Can anybody figure it out? I'm sorry? Okay, so let's look at this. So whenever anybody asks you that question, you want to look at an equation that involves that quantity. So I want the units of mu. Okay, so here's mu. Mu is friction force divided by the normal force. I'm writing N as Fn. This is the force that's measured in newtons. This is the force that's measured in newtons. And so newtons divided by newtons is dimensionless. This is a dimensionless quantity. It's just a number. Yeah? All right. From this equation, can you figure out what values could it take? what is the smallest friction force you could have? 0, very good. On a frictionless surface, it would be 0. So on your air hockey table, the friction force is 0, essentially. So mu k would be 0. What is the maximum value it can take? How would you increase friction?
Maximum value is the volume of force.
Okay, so if you wanted to increase the friction between this guy and this guy, what can you do to increase the friction?
Increase the weight.
So let's say you put super glue on it, the friction force increases. Okay, so if you bond the surface and it cannot move, then mu can be infinity. Okay, so mu can be anywhere from 0 to infinity. Okay, so mu really tells you the stickiness of the surfaces. Okay, all right. All right, so you saw that the static friction force is less than or equal to the maximum static friction force. So the maximum static friction force is mu s times the normal force. And once the object starts moving, it's a kinetic friction force. That friction force is called a kinetic friction force, and that's mu k times Fn. And of course, mu s is always greater than mu n. So mu s is always greater than mu k because the maximum static friction force is always greater than kinetic friction force. Okay. And like I said, I keep saying this stuff is important enough where they give you tables for various materials. Okay. And let me give you meaning to these things. Okay. So again, these are dimensionless numbers, and here are some values. So rubber on dry concrete is 1, and rubber on mu s is 1, and mu k is 0.8. Okay, and you guys know what anti-lock brakes are?
Stop your car from skidding when you brake.
What's that?
Stop your car from skidding when you brake.
It stops, prevents the brakes from locking on the wheels, so you don't skid. Okay, what you want is keep rolling. Okay, so we'll come to that in a second. So, when the brakes don't lock, what you're using is the static friction force. Greater the static friction force, faster you stop. Okay, now you guys are quite young, but let's say 20 years ago, car insurance companies would ask if your car had ABS, anti-locking braking system, and then your insurance rates would be lower. Okay. So anyway, all right, so let's figure out what this is. Okay, so this is rubber on dry concrete. Okay. So let's say here's a rubber block on a concrete surface. Let's say the weight of the rubber block is 100 newtons. So the normal force is 100 newtons. Okay, and let's say we got this rubber block moving. What is the friction force on it? The friction force is mu k times the normal force, and the normal force is 100 newtons, so 0.8 times 100 newtons, which is 18 newtons. Okay, so what this number is telling you is if you have a 100 Newton block, to keep it moving at constant velocity, you need a 18 Newton force. So that's what that's telling you. Okay. If you had a Teflon block sitting on steel, for a 100 Newton Teflon block, you need a 4 Newton force to keep it moving. That's what those things are saying. What is this number saying? If you have a 100 Newton rubber block sitting on the block, to get it started, you need a 100 Newton force, is what it's saying. Okay?
So,
So to get it started, you need 100 newtons. And once you start it, to keep it going at constant velocity, all you need is 18 newtons. Okay? That's what it's saying. That's what those numbers are telling you. Yep.
Will surface area with the same weight effect friction?
So we mentioned that. Remember, the most of the friction is coming from the atoms in contact there. Okay? And if you increase the surface area, you're not affecting the area of contact much. So that's why it's independent of the surface area. Okay, so I know the recording people can't see it. The friction on this is the same as the friction on this. Okay. All right. Okay. So we will be solving problems where objects are sliding downhill. Okay. So there are three forces acting on this object: the force of gravity, the normal force, and the friction force. Okay. Now, of course, there'll be drag force as well, but we are going to keep things simple, and we won't talk about the drag force for now. Okay. So there are three forces acting on the object: the force of gravity, the normal force, and the friction force. And if this guy is not accelerating, that means the sum of these three forces must be 0. Okay? Now, of course, this force is this direction is very inconvenient. So what we do is we break this force into these two components. Okay? So this force right here is not very useful. These two components are more useful. So this force got replaced by these two forces. Okay? And if this guy is not coming off the ski slope, then this force is being balanced by that. Okay? And if the component of the weight is greater than the friction force, he'll be accelerating downwards. If the component is equal to the friction force, then he won't accelerate, he'll move on at constant velocity. Okay? And that's the kind of stuff we'll analyze. Okay. Well, of course, this guy, if wants to accelerate, what he does is he pushes with the ski, and to this force he adds an applied force in that direction. Okay? And that's how he can accelerate down. But anyway, so this is how we'll analyze stuff. And again, the free body diagram is representing this guy as a point object, and there are the 4 relevant forces acting on it. Here's an interesting problem. Okay. And this is sort of a real concern. Okay, so here's a truck with a heavy box on the object. Now, let's say the truck was stopped and then it starts moving and it accelerates forward. Why isn't the crate being left behind? What is accelerating the crate? There's no engine attached to the crate.
friction against the crate to the truck.
Very good. So the friction force, what kind of friction force is that? Static friction force. The two surfaces are not moving relative to each other. Okay? And you learned that there's a maximum static friction force. Okay? So there's a maximum acceleration the truck can have. Okay? And if this static friction force is not up to the maximum static friction force, then you would leave behind the truck. I mean, you would leave the crate behind. But, no engine in a truck has that issue. Of course, if you attach a rocket jets to the truck, maybe you might leave the crate behind. Okay, so that generally is not an issue. Are you guys understanding that?
Yeah.
Okay. But here's an issue. Sometimes what happens is a wall will jump in front of the truck. Okay. No, this is real. People have died. I kid you not. Okay, so if something jumps in front of the truck, now the truck stops very fast, there's a large acceleration. And this static friction force is not able to stop the crate. This crate moves, if the truck was moving at 80 miles an hour, that crate was moving 80 miles an hour, and this guy gets crushed by the wall and the crate. So every time you see a heavy crate on the thing, it's always chained down. And that's against walls jumping up in front of the truck. Okay, not for the fear of leaving behind the crate. Okay, so this is real stuff. All right. Now you guys have all experienced this. We'll learn something important here. Okay, so let me review this first. Let me remind you of a couple of things. So we'll look at it. We'll get a top view. Let's say this is a circular road. Here's a car driving on the circular road at constant speed. Is the car accelerating? The speed is constant.
No, the car is not accelerating.
All right. There's yes and no answers.
Accelerating towards
Yeah.
the
Centrifugal
Right.
acceleration.
It's accelerating because the direction is changing, and so the car is accelerating. And Mr. Newton says, anytime you have an acceleration, I don't care what kind of acceleration, you need a force. Okay? So if your car is accelerating in this direction, you need a force in this direction. We'll call it centripetal force because the acceleration is centripetal. Well, what is providing the force? Well, the engine is providing a force in that direction. The engine is not providing that force. So what the heck is providing that force? This force. Gravity, this is a top view. Gravity is acting into the sheet. So here's the side view back again. Okay? So here's gravity. Gravity is not providing that force. So it turns out the wheels are the only other thing in contact is the wheels to the road, and it's a static friction force. Why is it a static friction force? Isn't the car moving? The car is moving in this direction. There's no motion in this direction.
There's more friction going forward than there is going around. Because since the wheels are pointing around, there's less friction in that direction, so the car moves that direction.
No, that's rolling friction. There's no motion along this direction, so that's a static friction force in that direction. Yeah? How did static friction force come about? How did any friction force come about? I'm sorry? Yeah, but at the molecular level, how did the friction force come about?
Is it dependent between the atoms moving around?
That's right. The atoms, the tire atoms are attracted to the road atoms. Okay? And so, by nature, well, what happens is, so all the tire atoms are not strongly bound. So if you were driving on a flat road, in a circular road, you'd leave some rubber behind on the road. How much rubber would you leave behind? So if every curved road in the country was flat, you would leave billions of dollars worth of rubber on the road. What do I mean by that? You'd have to change your car tires sooner and sooner. And that's how you can measure that. Okay, so it would cost the country billions of dollars. So how do you fix that? So you want the static friction force to be 0. Does that mean you can't have any curved roads at all? You'd have to have only straight roads. Okay, so we bank roads. That's why we bank roads, to save billions of dollars. Okay, now let's see what happens if you bank a road. What you want is a centripetal force in that direction. Okay, when you bank a road, there is a normal force. This component of the normal force is balancing the weight, and this component of the normal force is providing the centripetal force. And if the bank angle is right, this is large enough to provide the centripetal force, and you don't need any friction force. If you're going too fast, then you would need a static friction force, and if you're going too slow, you'd need a static friction force in that direction. But if you're going at the right speed, you don't need a static friction force, and then you save the country billions of dollars. Okay? And that's what it is. So we live in Daytona Beach. Have you guys ever been to the Speedway? They have 5K races there. You can run on them. The bank angle is 30 degrees. It's absolutely amazing. You got to run up the bank, and it feels like you're climbing up a mountain. And the minimum speed, I believe, okay, the speed there is, I think, 90 miles an hour or something like that, so for no friction. Okay. So if you throw an ice cube, you have to throw it at 90 miles an hour for it not to slide up and down. Yeah. All right, so banking prevents, you don't need friction forces if you have banked angles. Okay, so let's look at this. So n cosine theta should equal mg. N cosine theta should equal mg. So this is balancing that. And n sine theta is providing you the centripetal force. Okay. And of course, if you divide these two, tan theta is v squared by gr. Okay. Where r is the radius of the circular road. Okay. So if you're going at this, if you bank the angle at this, bank the road at this angle, and you're going at that speed, you don't need any static friction force. The component of the normal force is providing you the centripetal force. Okay? And so on every exit, you know, the engineers construct the road such that they know the radius of the exit, and they bank it such that if you drive at the marked speed limit, you don't need any friction force. Now here in Florida, it's not that important, but let's say up north, when roads freeze over and stuff like that, it doesn't matter. The roads can be as icy as you want. If you go at precisely that speed, you'll stay on the road. Okay? Be it at now there's something interesting about this expression. Can you see that? Does anybody see the interesting thing about this expression?
About the radius of the turn?
What vehicle is driving? The mass of the vehicle is not in there. So that's the same bank angle for the truck or a car or anything. Okay? Very neat. You guys understand? Of course, they can't bank it at different angles for different vehicles, right? All right, so on a flat road, a car can make a turn because, you know, the tires are in contact with the road, and even though you leave rubber behind, you still can use that static friction force. But if you were flying in air, you couldn't make a turn unless you bank. Okay? So a plane flying cannot make a turn unless it's banking, and again, the lift is perpendicular to the wing, and this component of the lift is providing you the centripetal force to make a bank. Okay. So, all right. Do you guys have any questions? I'll pause for a second. I have a few more slides to go through. All right. Now we'll talk about drag force. Drag forces are friction forces, except that drag forces are when objects move in fluids. Okay. So if you're flying to the right, the drag force is to the left, and if you're flying to the left, the drag force is to the right, okay? Like friction forces, they're always opposite to the direction of motion, okay? Now, there are two situations: the drag force being proportional to your speed and drag forces proportional to your, so two different situations, proportional to your speed square. Okay, so this applies. Okay, so for small objects falling slowly, such as dust particles falling in air, the resistive force is proportional to the speed. So for small objects, this is the drag force is proportional to that. Now this is important. For instance, during dust storms and stuff like that, you get a whole bunch of dust and pollen and all that kind of stuff suspended in air, and you want that to settle down fast so it doesn't give you allergies and this, that, and the other. Okay? So that can be an issue, and if it gets charged, it stays in the air much longer. Okay? But for now, we won't consider this. So we'll look at large objects where the drag force is proportional to the speed square.
Before we get too far on the drag force, could you go back to the static force for a second? I have a question.
Okay?
I guess I'm struggling to understand, because I thought static force is, it's always counteracting the motion, right? It's going the opposite direction of the motion.
Mm-hmm.
So how do you have centrifugal static force? What's the opposite force that it's counteracting?
Okay, so this guy wants to go straight, and you're trying to make him go in this direction.
Yes.
You're applying a force in that direction.
Oh, because the tires are turning, so that's causing the, okay,
No?
I understand.
So the only force that physically you can have is the static friction force in that direction. Because when this is turning that way, the acceleration has to be in this direction, in the centripetal direction, and static friction force, those atoms are the only ones that can pull them in this.
Shouldn't the static force be going in the opposite direction of that?
All right. So this is, so let's say the box wants to move in this direction.
Yeah.
And so the static friction force was, the atoms were pulling in this direction to prevent it moving in that direction.
Yes.
Okay. In the case of the car, it wants to move straight, but you are pulling the car in this direction to make it go around like that. And the only thing that can pull is the atoms attached of the tire attached to the road.
Okay.
Okay. So you have to pull in this direction to make it go around. So think of a ball attached to a string and you're whirling it around. You're pulling to the center. And the only thing that can pull it in this direction is the tires sticking to the road. All right, so drag forces, now we're going to, again, like I said, so this is through air. For small objects falling, such as dust particle, the resistive force is proportional to the speed. For large objects, it's proportional to v square, the speed square. So for larger objects such as skydivers and cars, drag force is proportional to the speed square. All right, so let's look at the terms. There's the drag force. So if this guy is falling in this direction, velocity is in this direction, the drag force is in the opposite direction. Okay. If you shot him up with a cannon and if he's moving in that direction, the drag force will be in the opposite direction. All right. So when you throw a tennis ball up, the drag force is downward, and when it's falling down, the drag force is upward. Okay. All right, here's the drag coefficient. Okay, and so that depends on the material and stuff like that. So if you want to fall, if you want this to be smaller, then you wear smooth clothing and stuff like that. Rho is the density of the fluid through which you're falling. Okay, so if you're skydiving, you're falling through air, and rho is the density of air. And of course, if you jump from real high, the density is lower, and so your terminal velocity at real super high places is higher than when you're close to the earth. A is the area of cross section. So If you're falling this way, this is the area of cross-section. Okay? The area of cross-section perpendicular to the direction of motion. Okay? And V square is that. Okay? Now, C, this is important. So the drag coefficient ranges between 0.5 and 2 for vehicles. So an aerodynamically shaped vehicle for Corvettes and stuff like that, it's probably close to 0.5. And for a UPS truck, it's close to 2. Okay. So that's what that is. Okay. Now let's talk about terminal velocity. What is terminal velocity? Yep. Yeah, through a fluid. Okay, so let's drop a cat for this experiment. Okay. When you first drop a cat, what is its velocity? 0. What is the drag force? 0. Okay? The drag force is 0, so when you first drop a cat, the only force acting on it is gravity, and so it accelerates at g and it starts falling faster and faster. But as it falls faster and faster, the drag force is increasing. Okay? So let's say its speed can increase such till what point can its speed increase? So as it's falling faster, the drag force is increasing. And as it's falling faster and faster, once the drag force equals the force of gravity, now the net force on it is 0. And so now it falls at constant velocity. And that's terminal velocity. Okay? So if you drop any object in air, once the drag force equals the force of gravity, then the net force on you is 0, and you reach terminal velocity. Okay? So if gravity is the only force acting on you, all objects will reach terminal velocity. Okay? So for instance, if a person, I mean, we are in the skydiving capital of the world, DeLand is, and if you nosedive, your terminal velocity is, I believe, 120 miles an hour, something like that, 180 miles an hour. And if you fall on your belly, it's about 120 miles an hour. What if you wanted to travel faster than 180 miles an hour in air?
Lighter.
I'm sorry?
That weight?
No. You'd have to have a jetpack. Okay. All right. So terminal velocity is, you reach terminal velocity when drag force equals your weight. Okay. And so you can rearrange these things, and so here's the terminal velocity. Again, yeah, you could add weight, but jetpack. Okay. So here's your weight divided by c, the drag coefficient. This is the fluid through which you're falling, and A is your area of cross section. So if you want to increase your terminal velocity, one of the things, easiest thing to do is decrease your area of cross section. Okay. So again, that's why falling this way, there's the area, and falling this way, that is the area. Okay. So this terminal velocity is much smaller than this terminal velocity. Okay. This is about 180 miles an hour. This configuration is about 120 miles an hour. Now this stuff is not just academic, this is important. Okay. So skydivers, again, this is the terminal velocity is that. So again, 10 miles an hour is about 25 miles, 10 meters a second is 25 miles an hour. So this is about 150 miles an hour. Okay, so if it rained baseball, for instance, baseballs would fall at about 100 miles an hour. Their terminal velocity would be that. That's quite interesting. See, that's about the speed at which a fastball is thrown. Yeah. Hailstones, they would be falling at about 35 miles an hour. Raindrops at about 20 miles an hour. See, thank goodness for drag forces, If you didn't have drag forces, the raindrops would be falling too fast and you couldn't walk in the rain. Okay. And you see, hailstones are heavier and they cause damage. And if the raindrop fell at that speed, you know, it would be hurting when it rained. Okay. So drag forces can be useful. Okay. Now, so we talked so far drag forces when we were falling in air. But let's say if you shoot a underwater missile, okay, now you're going through water. So if you shot a cannon through water, okay, then the drag force is proportional to the velocity. Okay, so the quadratic dependence of air drag upon velocity does not hold if the object is very small, it's getting very slow, or is in a denser medium than air. Okay, then the drag force is proportional, and then we find that the drag force is proportional just to the velocity, and that's, you also never reached high velocities, and this is known as Stokes' law. This eta, that's the viscosity of the fluid. The viscosity tells you that's the friction that the liquid, the friction force you feel when you're moving in the liquid. Okay, so for instance, eta will be larger for honey than for water. Okay, and so on. So it's the viscosity of the fluid, and this is the drag force. So for instance, when you pump oil through a pipeline, to get the fluid moving, you have to work against this drag force, and you have to do work. So if you can decrease the drag force, then the energy you spend pumping oil would be less. Okay, so you guys have heard that when they pump these pipelines in Alaska, they heat the pipes. Why do they heat the pipes? It has lower viscosity. You're heating the pipe to lower that guy, decreasing the drag force, decreasing your pumping costs. Okay. You guys have heard of Coriolis forces? You guys know that hurricanes go counterclockwise in the northern hemisphere. Okay, so what this is okay, so here's the following. Okay, so the Earth is spinning. How long does it take to go around? 24 hours. Okay, so you guys know the radius of the Earth is about 4,000 miles. 2 pi r, that's 6 times 4,000, that's 24,000 miles. So if you're at the equator, you're going at in a circle that's 4,000 miles big, and in 24 hours. So if you're at the equator, you're going at 1,000 miles per hour. If you're in New York, you're going in a smaller circle, so you're going slower. Let's say 600 miles per hour. So what is the speed at which this air is going? This air is traveling. So the air above the equator, what is the rate at which it's traveling? 1,000 miles an hour. What is the rate at which this packet of air is traveling? At 600 miles an hour. All right, so let's say now we create a low pressure here. We just put a huge vacuum there and create a low pressure. Okay, the pressure is higher here, so this packet of air would move in that direction. Except that this air is moving slower, this Earth is moving slower, so this air would actually get ahead of that piece of land. Okay. Now, you're saying, I mean, this air deflected in that direction. It appeared to deflect in that direction, but the air was going straight. It was the land that didn't keep up. this air is slower and this land goes faster, so this air lags behind. Now, because you were on a non-inertial frame, you are standing on land, which is accelerating frame of reference, you saw these guys being deflected, and because you were in a non-inertial frame, you invented a new force, a non-existing force to explain the deflection. And that's the Coriolis force. Okay. All right. So you can analyze this, and again, around high pressures, you would have a clockwise rotation. Around low pressure, you'd have a counterclockwise rotation, and this is in the northern hemisphere. In the southern hemisphere, it would be opposite. Okay. All right. So we read about drag forces, learned about drag forces and stuff like that. And if you were a bird, this would be very important for you to know. Okay. So for instance, if you're a geese and you're migrating, you're flying thousands of miles, and you have to spend a lot of energy to fly from point A to B. Okay. So if you flew by yourself, let's say you'd have to, I'm just going to make up numbers, a million joules of energy to fly from point A to B, solo flight. Now, if you fly as part of a team, if you're flying here, the drag force is still large on you, and you're spending a lot of energy. But if you fly here, the drag forces on you are less, and you would spend less energy. Okay. Well, but this guy is not happy. So that's right. So you rotate. Okay. Okay. Everybody spends some time there. Okay. This strategy overall, so each person, each bird would spend less than that energy in going from A to B. Okay. And that's why you see this on cyclists as well. When you have a group of cyclists going on bike rides, that's what they're using. Okay, so they're minimizing their drag. So the overall energy spent individually is less than if you went on solo flights. Okay. So even birds know this sort of stuff, and they take advantage of that. Okay. So by flying in a V formation, each goose spends less energy for the entire journey than it would have spent had it flown alone. Okay. And also by this formation flying makes communication easier as well. Okay. All right, so that finishes this chapter.